Okay.
Hello, and welcome to the Schiller Institute of Texas meeting. And my name is Diane Bettag, and I'm very happy to be here. After many years away from Texas, I find it to be a much more diverse place, and y'all come. So, I should just mention that last week's meeting was a real uplifting situation. We had Diane Sayre here from the East Coast, from New York, and she presented the Treaty of Westphalia outlook that prevailed after the Civil War here on the part of the administration of the United States, which, you know, we should observe today here in Texas. I had a conversation a couple of days ago with some people here about facts. My job here today is to give you a political update, and I sort of have this thing about facts because I think facts have to be put into a context. People have to understand what the philosophical basis is for figuring out which facts, you know, are relevant to what's going on in the world. And so we need a worldview that leads us to the truth. And the truth is that we've turned a corner on this attempt to overthrow our government. And that's what a lot of the facts that people are being bombarded with today actually come from. An attempt by the enemy to prevail on this question of overturning Trump's administration, and our drive that is led by the LaRouches to stop that overthrow and return the country to a sovereign and cooperative arrangement in the world. I wanted to give you a sense of this worldview, which has been resurrected and broadened and deepened by an American revolutionary named Lyndon LaRouche. He built a science of economy, and he built it upon the work of Gottfried Leibniz, which I just saw some of the political writings of Leibniz refresh my memory, you know, where he takes the golden rule basically as the standpoint from which you deal with others, other individuals and other nations. And this is very much the way LaRouche shaped his outlook even as a young man. Nicholas of Cusa, which was a gift from his wife Helga to our movement. Leonardo da Vinci and his machines, the Treaty of Westphalia, as I mentioned before, that ended the 30 Years' War, a concern for the interests of the other at the table. Matthew and his son Henry Carey, very important to the American Revolution, and Alexander Hamilton, whose economic science brought us the capability to rebuild our country after the Revolutionary War. His science was boiled down in a certain sense by some Russians who in the 90s read all his works and then discovered that he was in prison and wanted to ask him questions, came here and eventually created a unit of economics for measuring the capacity to increase the relative potential population density of an economy, which they called the LaRouche, a LaRouche unit, or the La. So through the years, LaRouche started in the 60s, in the mid 60s, building our movement around the idea of city building, that we needed nuclear plants, that we needed parity for agriculture, that we needed to modernize our productive capacity, and space exploration as a driving force. In the 1980s, he made a proposal for a high-speed rail connection between Berlin, Paris, and Vienna, which we called the productive triangle, and the European triangle. So the idea being that within this triangular area was the world's most productive, skilled workforce, and that could be a driving force for Europe. We could build up, as I indicated before, and cooperate and rebuild the world. And in the 80s, I'm sorry, in that same period, yes, he produced programs through our movement for the development of India in cooperation with Indira Gandhi, and for Africa, which he did in cooperation with the Japanese. We then in the 90s, in cooperation with his wife Helga, designed this Eurasian land bridge, which Helga then brought to China, and the Chinese ran with it. For 30 years, the Chinese have been running with it, and in the last 30 years, they have lifted 700 million people in their own country out of poverty, and now we have a few facts that the China's Ministry of Commerce spokesman reported yesterday, according to Xinhua, that trade between China and countries along the Belt and Road amounted to $786 billion, a 15% increase from the same period last year, January to September. Chinese businesses directly invested $9.6 billion in countries along the Belt and Road, up to 29.7% year on year. And investments made by Belt and Road countries into China stood at $4.24 billion, up almost 35% year on year. The system works. And, if we would do it here, and we're very, very close to doing it here, which brings me to the victory, which we are now hotly expecting. There was a major attempt to prevent Trump from going to China. He is now on the first leg of his trip to Asia. On the 8th, next Wednesday, he will start a meeting with Xi Jinping in China. This terrifies the enemy because Trump has been feisty. He's not caved in to the drive to force him off track from his promises before the election, his promises after, his intentions after the election, to renew our friendship with Russia, who have been our allies since the Revolutionary War, and to establish close relations with China, which was also our ally in World War II. And that's working. The Chinese and Russians are not paying any attention to all this crap which is going on in the media in the West about them or about Trump. And it's a wonderful thing, because if you know that what you're doing is going to help the most people, this golden rule is functioning there, that you do unto others and the Treaty of Westphalia idea, of the interest of the other, that's what you are concerned with, and that always benefits. It redounds to you. So that's the context for the deluge of facts that are pouring out the media, because it's a diversionary operation, so that people, don't realize the actual historic moment that we're living in. You're all preoccupied with sex scandals and, this guy's bad. And of course, Hillary, that's bad, right? But if you understand that what's just happened, she was on a TV program just yesterday, I guess, The Daily Show, saying, yes, of course I financed the dossier, that the MI6 produced, Christopher Steele produced, which was used by the FBI to convince Trump and everybody else that that there was that there was grounds for for overthrowing this government, basically. And that's an illegality which cannot stand and is not holding up. That the Democratic Party, Hillary, the DNC, and Obama's administration, cooperated with MI6, not the Russians, but MI6, British intelligence. This is a crime against the nation, and so that's the context, right? So I'm not really going to go through all of the details of this deluge, but there's just some really fun stuff. Donna Brazil's new book, which a friend of mine here just called The Revolt of the Hacks. I think it's very adequate. That Hillary stole the election from not only the election, but stole the nomination, stole the party, the DNC, the money, yeah, you name it, right? Mm-hmm. And Tulsi Gabbard has come out. This is a woman of some stature, who has been. She was a veteran of the war in Afghanistan, and she called today for a new leadership for the Democratic Party because of this scandal. So I just think, that this is a really excellent moment, and people should not be deterred from enthusiasm and hope at this moment, because the situation is in our hands, to turn. If Trump decides to bring the United States on board this new Silk Road, we've got it. The world has it, in the palm of their hands. With the United States, Russia, and China working collaboratively, this is beautiful. This is the only way to prevent World War III, right? I mean, because if the two major nuclear powers are working together, we can't be manipulated against one another by the empire. So that's basically what I wanted to say, and also remind you of this this wonderful dossier on this Robert Swan Mueller III, who is just about to meet his maker politically. Right? So that's what I have. I also would really recommend, in terms of understanding the philosophical basis of our movement, is that Will Wirtz gave a beautiful presentation at the Manhattan meeting, which we have on our website, LaRouchePack.com, in which he discusses the role of many of the people who I referred to as the basis for Lynn's economic policy and outlook, and also the economics series, which is on our website right now. We're now in the 5th class, and they're all archived on site. So people should do that. Now I would like to introduce our main speaker, Joel Dijon, who is going to speak about the women, or I guess it's called Einstein and the Girls of the Atomic City, Oak Ridge, Tennessee. I'm going to take it from Al Gore, right? Tennessee. Come on, Joel.
Grab my elbow.
Al Gore, really.
Podium to your right. To your right, behind you. Behind you. I'm sorry. There you go. There you go.
All right. Oh, the microphone's too high. I wanted to look at two examples of creativity before I get to Oak Ridge. And one in the very large and one in the very small. And they are connected by the mind and ideas of Albert Einstein. Now, again, before I get to Oak Ridge, I wanted to go through a little bit about physical chemistry. So, Mike, can you put up the table? Is it up there?
Yep.
Yeah, it's up there.
Okay, you all remember this from your high school chemistry. And I wanted to concentrate on just two of the elements, the first and the last. So the first being the most common element in the universe, hydrogen. And the last of the natural elements, element 92, being uranium. And Oak Ridge is the story about essentially uranium. Now, in order to get this whole table of elements, which is the basis of our physical economy, and if we look at just the way it's laid out, you have the hydrogen on the left, right?
Yep.
You didn't switch this around.
No.
Right. Now, you have hydrogen and helium are the main components of our sun. And there are trace elements of iron, chlorine in the sun's atmosphere. And so the question is, where did all these elements come from?
Mhm.
Now, the standard explanation is that most of these other elements, by the way, most of the universe, the visible universe, consists of hydrogen and helium, not over 95%. So where did these other elements come from? Well, the standard explanation is that you have the life cycle of a star. And a star that would be larger, more massive than our sun, has a very rapid life cycle. That the fusion occurs at the center of the star, where you have millions of degrees, and you have the basic element of hydrogen, the nucleus, which is a proton. I happen to have a proton
Oh, yeah?
here. This is about,
What a coincidence.
don't mind the color. It's about 10 billion times bigger than a usual proton. So the standard explanation for the fusion is that you have protons come together, fuse, and make the basis of helium. And in this process, a little bit of mass is lost and is converted to energy, which powers the sun. And in the life cycle of bigger stars than our sun, at a certain point, you run out of hydrogen and you start fusing helium. Now, the problem is that the protons have a similar electric charge. And as they come closer and closer together, since there are similar charges, they repel each other. So if you reduce the distance by half, the force repelling the protons increases 4 times. So you square the distance. So that as you get closer and closer, the repulsion increases until you reach a certain point called the Coulomb barrier, where beyond that point, what's called the strong nuclear forces take over and you get fusion. Now, in the larger suns, you fuse helium, then you fuse, you get carbon, you start building up the lighter elements. Now, at a certain point, for the larger stars, you reach iron, which is element 26. And at that point, the energy required to fuse iron is greater than the energy you get out from the fusion. So at that point, the fusion process cuts off and you get a collapse of the star. So the question has always been, where did these heavier elements come from? And it was thought that you have once the fusion stops, you have a collapse of the star due to its gravity. The outer gases of the star hit the core, cause a nova and then a supernova. And from that explosion, you get the heavier elements. Well, it doesn't quite explain it, because once you reach the stage of iron, where our sun, the core of our sun is about 20 degrees centigrade, 20 million degrees, to fuse the heavier elements, you have to get hotter and hotter. To fuse iron, you need billions of degrees centigrade. To fuse the heavier elements, you would need trillions of degrees. So where does that energy come from? Well, last month, we had the report of a collision in a galaxy far away. And this collision was not just a regular supernova. It's called a kilonova. And it involved the merger of two neutron stars, which were binary stars, which were circling each other. These stars had run out of their fusion fuel, had collapsed on each other, and the collapse was such that all the elements became neutrons. So that if this was a neutron star, the size of this marble would be the equivalent of the weight of Mount Everest. That's the density of a neutron star. And when the star collided, you had the release of not just neutrons, but a massive amount of energy in the form of gravity waves, which were predicted by Albert Einstein over 100 years ago. And we finally built the detectors. We were able to detect the gravity wave. Now, this one that was reported last month was the first time that not only was a gravity wave detected, but also gamma radiation, X-rays, radio waves were all emitted from the same region. So we were able to look at that region of the sky, and through the spectroscopy, we were able to see that not only was energy released, but elements like gold, platinum were created in this collision. And along with those heavy elements was uranium. Now, uranium is a very special element in that not only does it decay, now uranium comes in two basic forms. And I happen to have some uranium on me here. Hope I don't lose my marbles. Now, pretend there are 238 nucleons. So there are 92 protons and 146 neutrons in the nucleus of uranium. Now, in the early 20th century, we began to fill out the table of elements that Mendeleev had laid out back in the 1860s, 1870s. And through the work of Marie and Pierre Curie and others, we were able to see that there was radiation coming from the nucleus of elements like radium, polonium. And throughout the early 20th century, scientists like Enrico Fermi began experimenting to see what would happen if you use neutrons coming out of one element to bombard the heavier element. And the idea was that you would add neutrons to the nucleus of something like uranium, and the expectations was you would get a bigger element. You would get element 93, 94. And Enrico Fermi in 1934 won a Nobel Prize for that type of experimentation. Now, at that time, there were two ladies, one Ida Nodak, German, and Lisa Meitner, an Austrian scientist who was working in Germany. They looked at the available data from the experiment, and they said, well, you're not really getting a bigger nucleus, you're getting fission. You're getting the nucleus to split. And from the work of Einstein back in 1905, he had shown that mass and energy were equivalent. And what Lisa Meitner did in 1938 was she, using experimentation from Germany, which she had been forced to flee because she was partly Jewish, she looked at the data from her colleague Otto Hahn and said that, well, you're not getting a bigger nucleus, you're getting fission, and the energy out is exactly what was expected by Einstein's famous formula, mass times the square of the speed of light. Now, at that point, in 1938, people began to think, well, if you can release that much energy from a small amount of mass, this would be a tremendous weapon. And at that point, the US began looking into this. And right before Pearl Harbor, you had a letter from Einstein to Roosevelt, Franklin Roosevelt, requesting that work be done to look into this, because if the Germans were to get this bomb first, then they would win the war. So it turns out that on December 6th, Roosevelt signed the papers creating the Manhattan Project.
Really?
And it was named after the Manhattan Engineering District, which was supervising the project. Now, they had to create from scratch laboratories and facilities to convert the regular uranium into an enriched form of the smaller isotope, which was more prone to fission. Now, in order to do this, it required a huge industrial effort. And Roosevelt went to one of his colleagues, a Democrat in the Senate, and asked him, well, where can I hide $2 billion that it's going to cost to run this program? And the senator happened to be from Tennessee. He said, well, I have a location where you could hide this. And so that's part of the reason why it ended up. The other reason we went through a little bit when Marshall went through the Tennessee Valley Authority. And it turns out that the Tennessee Valley Authority produced not only the control of the Tennessee River, but it also produced a huge amount of hydroelectric power. And the director of the Manhattan Project, the military director, Leslie Grove, went to Tennessee and picked out an area that was not heavily populated, and basically said this will be the site of the laboratory where we will enrich the uranium to the required level to actually power the bomb. Now, this wasn't something that you just could do in your garage or some small operation. It required the construction of the largest building, bigger than the Pentagon, to do what they call gaseous diffusion, to increase the concentration. Because the problem they had, and I'll just go through a little bit, if you have uranium with 200 atomic weight of of 238, which is 99.3% of uranium on the Earth's crust is the uranium-238. Now, that has a half-life of 4.5 billion years. It emits alpha radiation, but it's not prone to fission. What you have to do to get a bomb, which they call the gadget, is you have to increase the concentration of uranium-235 from 0.7% to over 90%. Now, how do you do that? Well, there were all sorts of experiments done, but it was decided at this Oak Ridge laboratory, which eventually came to employ 75,000 people at the height of its operation. Now, since you had 16 million men under arms, what they began to do is they recruited a lot of the high school graduates, the young ladies from not just Tennessee, but from Pennsylvania, from New York, from all over the South and the East. And they were brought in and they were kept in the dark about what they were working on. Most of them had no idea what they were working on. But the idea of this enrichment is that if you have 238 and 235, chemically they are identical because they both have 92 protons in the nucleus. The only way to separate it is either they turn them into a gas and push them through a membrane, a gas membrane, or use electromagnets to accelerate the nucleus, and the lighter element will follow a different trajectory than the heavier element. And after thousands of runs of enrichment, you get the extra concentration needed. Now, to get back to the table, let's go to the second slide.
Explosion.
Now, this is not the one that was reported on last week. This is a different galaxy. But again, if you think of creativity, the universe is constantly creating new material. New stars are created. And even when the star dies, it creates new elements which seed the rest of the galaxy and seed the rest of the universe. So the particular explosion last month occurred actually 130 million years in the past. So this has been going on since the beginning of the universe, 13 or so billion years ago. And our sun, being relatively young, it's only 5 billion years, has had enough time to accumulate some of these elements in enough form so that once the Earth and the other planets formed, we had available on our crust the various elements, including uranium-238. So if you look at one of the labs, I want you to show the third. This is a picture of one of the labs at Oak Ridge. It's called, I think this is the Y12 building. So what these ladies were doing, and again, they were hired, some of them did clerical work, a lot of them did calculations to figure out the concentration. Some of them have had chemistry degrees, and they were used because you had to have a basis of chemistry in order to separate out, once you got the concentration, to separate out the uranium from the other elements. Now, the site, Oak Ridge, at its height, used as much electricity as the entire city of New York. So you're talking about, at the time, about 2 billion watts of energy. So throughout 1943, 44, they were figuring out what were the best ways of increasing the concentration. And they had three different methods. One was electromagnetic separation. One was separating through gas membranes, gas diffusion. And the other was by heating up a gas and running it through various membranes. It was called thermal separation.
They were increasing the concentration of the uranium, or?
Uranium, again, you have uranium-238, which is 99%, and you have uranium-235, which is the one you want. And that's only 0.7%. So what they would do is they would turn the uranium, which was an ore of a yellow cake, and they started out with about 3,000 tons, which was imported from the Belgian Congo by way of Canada. So they started out with 3,000 tons, and by the end they had produced about 100 kilograms of enriched uranium, a concentration of uranium-235 above 90%. Now, the woman who wrote the story about the girls of Atomic City, she goes through how they built this city from scratch. They had rail lines going in. They had all sorts of operations going in. And the people around Oak Ridge kept looking at what was going on. They said, well, train loads of material, pipes, magnets. And some of the magnets, they had to melt silver from Fort Knox because there was a shortage of copper. And they used the silver to make the windings around the magnets, to make the powerful electromagnets to separate the elements. And so you had this massive operation going on, and nothing was coming out. So most of these plants, you had metal, aluminum, rubber, all sorts of material going in, and you had tanks, airplanes, trucks coming out. But in Oak Ridge, the final product fit into a few briefcases. And these briefcases contained the enriched uranium-235, which was then sent to Los Alamos, where the gadget, as they called it, was put together. And again, there was such secrecy that some of the scientists who visited the facilities, they would come in under an alias, and they would go in to inspect what was going on. And there's an incident that she writes in the book about Ernest Lawrence from Berkeley, University of California, Berkeley, went to check on his calutrons, which are these huge electromagnets. Now he had a group of scientists and engineers that he brought along to operate these things. And they had a parallel operation being run by the young ladies who were trained. And running in parallel, there was more output of enriched uranium from the young ladies. Most of them had just high school degrees, than from these top-notch scientists and engineers. But she reports that you had no computer controls. They had to operate the gauges, and what they found was that once the scientists and engineers went in there, they would fiddle with the gauges all the time. Where she reports that if you gave instructions to these young ladies, they would, unless they were totally confused, they would follow the instructions, and they would actually outperform some of the more college-educated type. So for about a year, they ran flat out enriching the uranium. And by the time they had enough, they shipped it to Los Alamos. And it wasn't until the bombs were detonated over Hiroshima and Nagasaki that most of the people at Oak Ridge even got a whiff of what was going on. So again, if you look at the creativity, you have a universe which is creative, which creates all the material that we use in our physical economy. But it takes the individual mind of someone like an Einstein to figure out, well, how does the universe work? How is energy created in the stars? And how could energy be created on Earth? Now, it's tragic that the first use of this fire, this energy, was during war. But immediately after the war, we had the Atoms for Peace, where the energy released in a controlled fashion was used to create not only atomic energy for submarines, but atomic energy for civilian uses. So under war conditions, the resources were provided to make the breakthroughs, to actually use the discoveries that were made earlier, to actually have a driver to obtain the energy output that was available according to the physical laws of the universe, but would have never been achieved unless you had a government-directed program to concentrate the scientific, the industrial, the military manpower needed to reach the breakthroughs that we achieved in a matter of just a few years. Now, that is an example of what we should do to reach a controlled fusion for the future. We're never going to get there by just nickel and diming. We have to have a concentrated effort like we had with the Manhattan Project. This time, instead of running an operation to produce a weapon, we have to run an operation to produce the power necessary to drive energy here on Earth as well as in outer space. So I'll leave it there. And if you have any questions on Atomic City or...
I have a question, Joel.
Yeah.
Did the Germans have a program at the same time?
They did have a program. But you see, here's the problem is that Hitler hated Jewish science.
Oh.
And he actually hated Einstein.
He did, yeah.
And there were pamphlets put out about how relativity was a Jewish plot.
Come on. Really?
So here you have the top scientists
Oh
like
my Lord.
Edward Teller,
Oh,
Einstein,
right.
some of the top scientists who were all educated in Germany.
Jeez.
The lucky ones escaped
Right.
in the early 30s,
Yeah.
and a whole bunch of them ended up working at the Manhattan Project.
Hmm.
And the only reason why Einstein himself did not work on the Manhattan Project is the FBI had an open file on him, and he couldn't get a security clearance to work on the program.
He was a troublemaker.
Now, in the book, the author, Denise Kiernan, she mentions that at the end of the war in Europe, the German scientists who were suspected of working on a bomb, like Werner Heisenberg and others, were captured, and they were kept in a house, a farmhouse in England, which was bugged.
Oh.
And they were listening because they wanted to know, well, how far did these guys get? And it turns out that the German atomic bomb project was completely starved of funds because Hitler's idea was to win the war in just a few years, and he didn't want to spend money on some fancy program that would take years to develop.
Wow.
So it turns out that the Germans were not anywhere near the point of actually building a bomb.
Mm.
And the same with the Japanese.
Mm.
There were Japanese scientists who were capable of working on this, but again, the emphasis was to build off-the-shelf weapons that we have now, concentrate on winning a quick victory, and you don't spend money on some fancy research project.
Like now.
So what was the connection with these ladies to the ladies earlier at Harvard doing the calculations to the ladies at Langley who later were doing the calculations and work on the space program? What was there overlapping of some of these individuals?
Not that I know of. No. The only connection was that there was a pool of talent available that could be brought to bear on a problem. And a lot of them would be working on calculations. The author has a report of one woman who was a chemist. And she was brought on board, and she was instrumental in working out some of the various operations needed to separate out the uranium before enrichment. So as far as calculations, there weren't as many in Oak Ridge as in Langley and as in Pasadena. But the idea was you have this pool of talent. You can be brought in, given simple instructions, and you can concentrate and make the breakthrough.
And what year is the Oak Ridge?
It opened in the December of '42, and they broke ground in the spring of '43.
So this is while the war is still going on.
Oh yeah, in the middle of the war. And they built the city in the area of Oak Ridge. There were about 3,000 people in that area. By the end of the war, there were 75,000 people they built the city. Now it was a little like Houston in that they built all these buildings, but they didn't build any sidewalks. So she reports that a lot of these ladies were brought in. One woman from the Manhattan office, she was transferred to Oak Ridge. She was given her orders, basically, although she wasn't in the military. She was told, go to this train and we'll tell you where you're going when you get there. And so she had no idea where she was going. And she ran into some other ladies that were going in the same direction. And when they got there, and she had her finest dress and new shoes and everything, and she reports she gets out of the car that picked her up. And the first thing is she sinks into the mud.
Oh, Lord.
And that was a condition throughout the war because they didn't build all these fancy sidewalks. But they were using electricity, pipes, metal. And they had to figure out the width of the membranes so that you could, because you would have to convert the uranium into a gas and then push it through the membranes. You had to figure out the width of the membranes that would enhance the diffusion of the lighter elements and retain the heavier uranium-238. And there's only a 1% difference in atomic weight from 235 to 238. So it was a very fine calculation. And so as far as calculations, it was mostly concentrated on the chemistry needed for the separation.
Now, how long did it take them before they made a breakthrough? I mean, this was a process, right?
Yeah, about a year.
Uh-huh.
And so things, they didn't run things in series to say, well, if we get this, then we'll build additional plants. They ran things in parallel. So they had this idea of electromagnetic separation, gas diffusion, thermal, and they built it in parallel. So at first, they were only getting a few tenths of a % increase in concentration. And it wasn't until 1944 that they actually had enough of the material to work with.
Wow.
And like I said, by the end of the war, the output was about 100 kilograms, about 220 pounds.
Sure.
And they were doing the calculations in Los Alamos to figure out how much of the enriched uranium you need to get a chain reaction going. Because with the uranium bomb, what they would do is there's something called a critical mass, that if you have enough concentrated enriched uranium, you get neutrons, which will cause one atom to fission, to split, and it will cause a chain reaction. But to get a continuous chain reaction, you have to have a critical mass. So what they did for the uranium bomb was they had two halves, and they used a shotgun type rifle system that when they were about to use it, they would fire the chemical explosives to bring the masses together, and you would have a critical mass, and then you'd get the explosion.
Wow.
So I have a question. So what do you think, given the shift that's been made in the world right now toward China, the Belt and Road Initiative, mutual cooperation, how could you take a national program like this, which was not just, obviously not to increase our military capabilities and our building of bombs and so forth, but it went even further in terms of, well, I guess the question is, you're talking about the need for using this as an example for a real science driver for a national mission. The science driver that now would really have to take off with the space program. How would you apply that to an international mission of cooperation?
Well, what you would do is you'd lay out what the goal was, because they had a very clear goal. They knew that they needed a certain concentration. They knew that they needed a certain amount of the enriched uranium. And then they figured out how they would do it. If you were to try to, for instance, complete the idea of a fusion rocket, we have the idea of how to build it. And we have labs like Princeton Plasma Laboratory, and you have the MIT laboratory and laboratories all over the US, where they're working with literally pittance, a few $1 million here and there. If we follow the model of the Manhattan Project, you would bring these teams together and money would be no object.
Right.
That you would pour the resources in instead of having yearly budget cuts, and you would pay these researchers so they can concentrate on producing a breakthrough. And we would get rid of the limitation of collaborating with China.
We have to hide it.
And well, maybe we'll get it out in the open when Trump goes there next week.
Yeah.
But if you were able to bring, because if you look at the Manhattan Project, it was an international effort. I mean, you had Enrique Fermi, you had Teller from Hungary, Fermi from Italy, Einstein originally from Germany, and you had Ernest Lawrence from California, Robert Oppenheimer. So you had this concentration of international scientists who were mostly refugees from Hitler's Germany. So instead of just having a bunch of refugees, if you had a collaborative effort, then you would be able to bring in the best minds from Russia, China, France, even Britain, and concentrate and give them a blank check, because the amount of output you would get from a breakthrough would more than pay for any amount of money you spend on the research. So if we look at the Manhattan Project and the Apollo project in the space realm, what you had is the goal was set, and then the resources were poured in, and then the breakthroughs came from that concentrated effort.
Joe?
Yeah.
Somebody told me yesterday that nuclear energy was just an accidental spin-off from the work on the bomb. And I didn't really know anything about how peaceful nuclear energy was developed. Can you say anything about that?
Well, the way it was developed is Admiral Rickover was brought in, and he used the breakthroughs from the Manhattan Project to build the first light water reactor for a nuclear submarine, the Nautilus, in 1954. So it wasn't directly a civilian program, but it was a concentrated effort to get the power for a submarine that could sail under the Arctic Ocean and go around the world without refueling. And that program was used as a model for the civilian nuclear program. So there was dual use. Anything you could use in the military. For example, you could use a rocket to launch an intercontinental ballistic missile or launch a satellite. And as a matter of fact, the reason why the Russians got to space first is because in the 50s, they were not able to shrink the warhead to a small enough area. So they had these huge rockets to get the big warheads, and they converted that rocket to launch a satellite. So it was a military program that opened up the way for civilian uses.
It's a principle of the oligarchical control over society that the oligarchs will only allow research into things which will keep them in power. And so therefore they exclude everything but military investments. But smart people are able to take the military technologies and deploy them in other ways.
Yeah, because once you make the breakthrough, I mean, if you look at what was done to detect gravity waves, well, it required lasers, it required seismographs, all sorts of electronics. Well, the laser came from the spin-off from the Einstein's paper on the photoelectric effect. So you can use a laser as a weapon, or you could use it to measure distances. And you can use that as a window on the universe. And one of the reasons why a lot of the science programs were taken down in the US is because once the Soviet Union collapsed, it was thought, well, we don't need to build up science because our enemy has collapsed. So we can just become an internet economy. And the internet was built through a defense advanced project research agency to survive a nuclear war.
Great.
Because they wanted to have computer centers that would not be knocked out by a nuclear strike, that could function when sections of it were knocked out. But the idea, like Kraft Erica went through, is that we've reached a point where our technology is such that if we have a war between the great powers, it will lead to our annihilation. How can we get nations to collaborate to use that technology for a greater mission? And that's where the space program comes in. Because you're not going to occupy Mars as a base against North America or something.
How about against Jupiter?
Yeah, maybe he is Zeus after all. So you want to send those lightning bolts.
Well, another point about the war economy is that it forces people to look at resources and their allocation in a different way. And it's not like the prejudice of the time had everybody saying, "Okay, let's send all these girls, girl power, send them to do all these calculations because that's what girls are good at." No, they use these women and their formidable talents, which were overlooked until then, because all the guys were out at the front with rifles.
Well,
in their hands,
it's not all the guys. Actually, when she goes through the book, the Girls of Atomic City,
yeah,
she goes. There were some men who were about to be shipped overseas, and because they had certain technical background, they were given orders to go to Oak Ridge. So there were some, it wasn't all women. There were some men involved.
I apologize for overgeneralizing.
Yeah, but I get
Those
the
were some
point.
lucky guys, I would think. Just offhand. But again, the Nazi approach was not so much to mobilize free women, but to use slave labor when we're confronted by the same sort of problem. And slaves have for some reason, they have a motivation problem.
Yeah.
That's why I listen to a lot of radio. So some of these late night programs will go through how the Germans had all this advanced science and they could actually build the flying saucers that went to the moon. And I keep thinking, well, damn, if they had all this technology, why didn't they win the war? Well, they didn't win the war partly because they drove out all of their top scientists, including Lisa Meitner.
Yeah.
And that's an interesting case there because Enrico Fermi was convinced that if you take a neutron and shoot it into a nucleus, and in the 30s, early 30s, it was thought that the nucleus is unbreakable. That the word atom comes from the Greek. It means you cannot section, you cannot separate this. So the assumption was that if you shoot this neutron, you get a bigger nucleus. So in 1934, Enrico Fermi was doing the experiment. He was actually getting fission, but because he was looking for a bigger nucleus, missed it. So for 5 years, most of the men who were running these experiments were so convinced that their assumption was right, that you get a bigger out because it was assumed you can't split the atom. That it took actually 2 women, Ida Nodak and her husband, who was also a chemist, and Lisa Meitner, who looked at the same data and said, well, no, Dummkopf, this is not a bigger atom. You're splitting the atom. And and Lisa Meitner, she's an interesting story. And this is the case up to the 1950s. She was brought into Berlin to work in chemistry but she was not allowed to work in the chemistry building. She had to work in the basement because women weren't allowed in the upper echelon. So it was the first basement.
That first basement project.
And the same thing, well, Oak Ridge being in Tennessee, there was still segregation.
Yeah.
So the same thing with African Americans. They were brought in to work in the program, but not in the engineering part. As a matter of fact, the other name for Oak Ridge was the Clinton Engineering Works, because Clinton was one of the towns nearby. He wasn't named after Hillary or anything.
Just the explosions.
Yeah.
About the time, well, right after the cold fusion, the case of cold fusion was put out as a whole class series in history of key scientific developments. You know, Lynn put this whole report out, and he looked at the cold fusion as maybe an example of getting beyond these Coulomb barriers in a manner different than just overpowering them. And I thought about this a little when these stars collided also, just in terms of some of where the research is today. Because I know in the course of that, Lynn had posed to Bostic and others in terms of where do these heavy elements come from in our own solar system. And Lynn had described in a question an approach where you look at this kind of distillation in the outside the sun. We actually have these heavy elements formed. And I was just wondering if, from your own reading, is there any further development on that cold fusion approach and this, you know, getting around these Coulomb barriers in that form? How does that relate to some of the operations that took place in this example of the colliding stars and just this frontier of science? Where are we actually right now in terms of some of these breakthroughs and these bigger understanding the dynamics as opposed to just being able to measure after the fact?
Yeah, now, as far as the cold fusion, when that first occurred, and this was I remember it was March 23rd, 1989. And these two chemists were separating because if you have water and you run a current through it, you can separate the hydrogen and the oxygen. And the hydrogen will concentrate in one of the electrodes and the oxygen in the other, and then they'll bubble up. And what they were getting, because they were using heavy water and they were using palladium, they were getting more energy out than they were putting in the form of electricity. And the immediate reaction of the physics establishment was that this is impossible. If you were getting energy out, you would get it in the form of neutrons. And the neutrons would have killed the operators of the device. So immediately it was frowned upon. Now, when Lynn looked at it, and I remember thinking about this in the early 90s, is that this is right around the time of the moon model of the nucleus. And Larry Heck did some work on this, but outside of what we published, nothing has been done on the actual geometry of the nucleus. But if you go back, can you go back to the periodic table? Because there's an interesting characteristic here. If you look at hydrogen and helium and lithium, which is number 3, those are the most abundant elements. But the next most abundant element is carbon, not boron. Boron is from the fusion of Bush and a boron. So it's very, very rare. But if you look at carbon and you think about Moon's bottle of the nucleus, well, carbon has 6 protons, and if you arrange them in the construction of the octahedron, that you have a completed shell, which is the most stable. The next most abundant element is oxygen in the universe. And if you look at oxygen, the way Moon had modeled it is that you have 8 protons. And if you put 8 protons on the vertices of a cube, you get the oxygen nucleus, which is the most abundant after carbon. And if you look at iron, iron is a completed octahedron, cube, and icosahedron with the completed shells of the protons at the vertices. So Moon's model actually explains a lot of the abundance of the periodic table. But as far as work being done nationally, there are some labs still working on what they call low energy nuclear reactions, because the cold fusion was so dispersed that they call low energy nuclear reactions. But if we were to have a crash program for fusion, you would want to fund something like cold fusion. And as far as the heavier element, I remember that Daniel Wells had built something in his lab where you would have the
smoke ring machines.
Yeah, so you would have the reactions occurring in the rings to create the heavy elements. But as far as the concentration of elements, I think nothing has really been done on what Daniel Wells was working on, or Bosnick, or even Fleischmann ponds.
But it's hard to beat 2 neutron stars colliding.
Yeah, because if you think about it, when you have a say instead of a proton, this is a neutron star. And again, it's the weight of our sun, but the diameter of a neutron star is about the size of Manhattan, about 12 miles. So the sun is about 1 million miles, 840,000 miles in diameter. So take that weight and compress it to 12 miles. And if you have a binary star system, and if they both have the same weight and they go supernova at the same approximate time, and they both become neutron stars, they're not emitting a lot of visible light. But as they orbit each other, the orbit decreases. And what was detected by this LIGO, which is the Laser Interferometer Gravity Wave Observer, is that by the time they came close, they were rotating at 1,000 times a second.
Wow.
And when they collided, you had one of the stars was about a 1.5 solar masses, and the other star was 1.6. So you combine that, you would expect, so you get 3 solar masses. But what they measured is that when they combined, they ended up with 2.6 solar masses. So imagine half of the mass of the sun just disappeared. But it went into energy in the form of a gravity wave and gamma rays and the production of these other heavy elements X-rays and radio waves. And by the time the wave reached the detector, one in Hanford, Washington, and one in Livingston, Louisiana, measured the difference in length by the vibration of less than the width of a proton.
Wow.
That's the sensitivity of that. But if you think about half a solar mass multiplied by the speed of light squared, that's the amount of energy that was released, which is equivalent to what the sun would put out over its 10 billion lifespan, 10 billion year lifespan.
That, you're saying that energy was produced in a moment?
In
Wow.
a second.
Really?
And by the way, they convert the signal, they turn it into a sound signal. And when they had the black holes collide back a couple of years ago, the signal was around 250 hertz, almost 256. And this one, the signal, because they were less massive, it had a higher signal. They actually said it was 2 octaves above middle C. So the universe was singing to us.
Yeah, wow. Sounds like it.
Going back to Fermi, now he wasn't totally on the wrong track about heavier nuclei, right? Because there are the transuranic elements, plutonium, etc. So how much plutonium research was done at Oak Ridge, if you know? There were the seed crystal for what was done at Hanford. So there was plutonium work done at Oak Ridge, but it was transferred out to Hanford. Thanks.
And does this have the transuranics?
Yes, it does, yeah.
Okay, plutonium is element 94. And that's a man-made, it's not produced in nature. Or if it is, it's a very small amount. And the second bomb, the one in Nagasaki, was a plutonium bomb. They had the plutonium and they imploded the bomb to get the critical mass. Now, plutonium, a different isotope, is what powered the Cassini spacecraft near Saturn. And it's what powers the Curiosity rover. Now, I didn't bring it, but if you have a smoke detector that you can take from the wall, and you look at the back of the smoke detector, and it has the radiation symbol on it, because it uses element 95, which is americium, which comes from the nuclear reactors. And it's used because it emits alpha particles at about 3,000 times a second. But you only have a few micrograms in there. And if there's a smoke near the detector, it will block that beam of alpha rays and trigger the alarm. So every household in America probably has a transuranic element in the house. And I don't know how many people have been saved, but it's probably in the thousands by smoke detectors.
It's right next to plutonium, the one that everybody's afraid of all the time.
When Ponce and Fleischmann were driven from the country, I heard that the Japanese were then funding their research. Do you know?
Well, Pons went to France, and Fleischmann, he died recently, well, a few years ago. But the Japanese were actually, when I remember back in '92, there were 3 labs in Texas that were working on cold fusion. One at A&M, one at Austin, UT Austin, and there was another one in Lubbock. And when Carol White was still editor of 21st Century. She came down here, and I took her up there to A&M, and they were working on it. But the professor we met with, John Bachris, he was the head of the chemistry department. And he was actually detecting tritium in his experiments, which indicated some kind of nuclear reaction. And within a few months, he was driven out of the chemistry.
Go to France.
He was there. I don't know why. Well, he died in the mid-90s also. But here you have the top chemist at Texas A&M was forced out of his position. Not because of a sex scandal, but because he was working on forbidden science.
Hey, Joel.
Yep.
So, I mean, we know that this president is more open to pushing breakthroughs in science and technology. You know, I missed an earlier part of your presentation, so I don't know. Do you have anything to say about any kind of feedback you've got, or any kind of picture we have of an orientation that's interested in pushing this through, or do we expect to drive this forward with the breakthroughs with the U.S. joining the new Silk Road?
Well, the most significant indication was, I think it was last week, that Michael Griffin was appointed to a deputy defense secretary. Now, he should have been appointed NASA administrator, but he wasn't. But he's someone who, when he was NASA administrator, was asked about global warming, and he says, "Well, he's a denier. He doesn't believe it." Right. So that's an indication that you have somebody competent who's going to be in charge of the Defense Department scientific research.
So he's the deputy director of the Department of Defense for Scientific Research?
Right.
Okay.
And there was a slug in the briefing last week, I think it was. But that's the only indication. Now, next week, we got a email from Marsha Maluk that there's going to be an energy conference. But one thing I noticed about this is the Heartland Institute. And it sounds interesting, but the list of speakers is about natural gas, coal, and there was nothing about nuclear power.
Which is interesting given what Energy Secretary Perry has been saying in terms of direction for nuclear, that they trying to just ice that out of the discussion. Maybe they'll put it in there, maybe, but it was, I mean, the fact of the matter is that the administration is actually talking about it more directly.
Well, they're actually saving nuclear plants right now.
Yeah.
They're not letting them shut down.
Yeah, but there's no push for things like the fourth generation nuclear power plants. I mean, if you look at one of the differences between Texas, Florida, and Puerto Rico, is we had nuclear plants here.
Yeah, that's true.
In Florida also. But Puerto Rico is totally dependent on oil for its electricity.
Now they want to put up solar panels.
Well, one of the good things I noticed, there's not much good that I can see from these tax cuts. But one of the good things, they're eliminating the fees, the discounts for electric, not just solar panels, electric cars and stuff.
Yeah, Tesla Motors stock plunged on news of that. Yeah.
Okay.
For Elon Musk.
Oh, I feel sorry.
Oh, yeah.
Poor billionaire.
Uh-huh.
Ill-gotten gain, I have to say.
Yeah, he's an example of hype.
Yeah.
Too much hype, because he's talking about using chemical rockets to go to Mars, using solar power, batteries.
Okay, Joel, thank you.
Thanks.
There you go.